So in this unit, we're going to talk a lot about this idea of chirality. And chirality is going to come from the fact of having a unique arrangement of molecules in space. And the different arrangement and things in space are going to have some different properties. And we're going to do a lot of like characterization of those. Now, you're kind of already familiar with the example of stereoisomers. We're familiar with the broad term of isomers, meaning things that have the exact same amount of atoms, same number of carbons and hydrogens, but they're connected differently. Stereoisomers are a lot of things like we think about when we think about like our chairs, for example, from our last unit, where we saw, like, for example, the difference between like a cis and a trans, where you have the same stereochemistry or different stereochemistry for your groups. And those can have drastically different properties. Here in the chairs, you have one that has an axial and equatorial, or the other one that has two equatorials. And as you change the arrangement of stuff in space, you can get a lot of different types of properties. And we're going to be exploring a lot of that in this unit. So we're going to start by introducing a few terms. And the very first one is going to be the idea of an enantiomer. And we're going to talk about enantiomers and a lot more in a subsequent video. But this comes from the Greek word meaning opposite. And our formal definition of an enantiomer is a non-superimposable mirror image. We'll focus in a subsequent video about what those look like in terms of actual chemical structures, but your hands are a perfect example of enantiomers. So if I jump out to here, so if I think of my two different hands, they are mirror images to each other. I have my pinkies on the same side, my thumbs are on the same side, and they kind of match, the same as if you were like looking in a mirror. So they're mirror images of each other, but they're not superimposable. And the word superimposable means that you can take and then lay on top of each other, and they match perfectly. They're like imposable, or they match. So if I take my two hands and I go and I put them on top of each other, I see that my thumbs are on in the camera. My thumbs are on the wrong side. There's a specific handedness where my right hand and my left hand are different. They cannot be imposed on top of each other. If I do it like this, I have a palm up versus palm down, and uh, they are also therefore like not matching. So just like my right hand and my left hand are different, they look similar. They both have the same number of like digits or fingers, similar lengths and things of that sort. The way in which they're connected in space is different. My thumb are on the right side or the left side, for example. Molecules can have that same type of unique like arrangement of atoms in space, and this is going to bring about this idea of chirality. And chirality is going to be a geometric property which arises from a stereocenter. Now, a stereocenter is going to be an atom, a lot of times carbon, but doesn't have to be carbon, but a lot of times it's going to be carbon, that's going to have four unique or distinct groups around it. And those groups are going to be arranged in a certain order. And we're going to be able to define the handedness, and that word hand from Greek is actually where that word chirality comes from, to describe that specific arrangement of atoms. And one of the questions is, why does it matter? I have here just a handful of examples of some differences in some properties for different structures. And in here, we're going to see a bunch of different terms. So we're going to have L and D, R and S, plus and minus. These are going to be a bunch of different descriptors that are going to describe the difference of your structures and how they're situated in space. And we're going to be getting all the kind of like fundamental knowledge in this video to be able to define those R and S, plus and minuses, L's and D's, and in class we'll focus on the actual like description for those. The key difference is in each of those letters or signs, there's a difference in the arrangement of atoms, much like how my right hand and my left hand is a little bit different. And we can see a huge difference in terms of properties. So just a small set of examples here. We can see in terms of flavor of an artificial sweetener. One is a sweet taste, meaning it's an effective sweetener. The other one is tasteless. In terms of odor, here's an essential oil, and I have the two different structures there. One smells like spearmint, and the other one smells like caraway. In terms of effectiveness, and this has a huge impact in terms of drugs and medicines. And we're actually going to do a real world application that's going to surround that. Here is an antidepressant drug where the plus form which has one specific arrangement of atoms, is an effective antidepressant, and the other one has no impact. Outside of just effective versus no impact, there can also be huge safety differences. So here's at the bottom, we have a penicillin derivative where one of them is used to treat rheumatoid arthritis, and the other is actually toxic. So you have to be really, really careful about how your atoms are spread out because they can drastically impact how impactful it can be, or potentially even dangerous it could be to a potential consumer. And the idea of having these chiral centers, these specific atoms that have some stereochemistry defined, some wedges and dashes, and a variety of different groups attached to them, are ubiquitous. They're all over, especially in bioactive and medicinal compounds. Just a little bit of data I pulled. So between 2020 and 2022, every single new drug that was approved by the FDA had a chiral stereocenter. And actually, if we look over a decade from 2013 to 2022, there was actually only 10 out of 278 drugs that were approved by the FDA that did not have defined stereochemistry. So that's less than 4% of drugs didn't have this kind of like defined property of groups. So we're looking at over 96% of drugs having this like unique types of structure. So this is something that's used a ton in the medicine field. And we're going to learn how we can actually use our descriptors, these pluses and minuses, R's and S's, L's and D's, to describe our molecules. And this is going to be kind of like parts of like their name in terms of like their nomenclature. Now, in order to do that, we need to first get a little bit of our kind of background on how we're actually going to rank our different groups. And these are all going to come from a collection of scientists who came up with these rules to describe our stereo center. There's 3 of them, and this is just their last names, the Cahn-Ingold-Prelog Rules. And I just combine them together and call them the CIP rules for short. And CIP is going to be a kind of process in which we look at a molecule and we are going to rank all of the different groups that are attached to them, and then use that to be able to eventually get to like that R or S, or that plus or minus, that D or L. So our focus today is just going to be understanding our CIP rules. So for the rest of this video, I have a handful of different rules and then kind of talking about some examples that are associated with them. So the first thing that we do need to happen is we need to have a chiral center. And a chiral center is going to be a atom that has 4 unique attachments. So down here at the bottom, I've not specifically called this a carbon, but this circle could be a carbon, could be any atom for that matter. But an atom that has 4 unique attachments. So here we have a methyl group, a hydrogen group, an alcohol group, and a bromine. So 4 unique stuff. And the way in which they're situated in space can vary. So what we're going to do is we're going to have a ranking system for all 4 of those different groups. We're going to rank them 1, 2, 3, and 4. And then that ranking is what we're going to use in class to be able to figure out, for example, our R or our S. Now, our very first kind of rule is when we're looking at each of those different atoms, we are only going to look at the very first thing that is attached to our chiral center. So in this case, our carbon that I've drawn in. So if I look at this bottom here, I have this carbon, this hydrogen, this oxygen, and this bromine. So those 4 things that I just highlighted here in yellow, those are the only things which we're going to consider at the start. All the other hydrogens that's connected to like the alcohol or the methyl at the bottom, we are not considering them at all. We are only looking at the very first thing that is connected to each of the chiral centers. And when we look at those, we're going to try to rank them by atomic number. Atomic number you can see on the periodic table. I have just a little snapshot of some of the most common ones. So you'll see like carbon, for example, is at 6, kind of on our low end, and then a bunch of other ones kind of listed there. So if I look at this example here, I see that the things that I highlighted are all unique. I have a carbon, a hydrogen, an oxygen, and a bromine. So because of the fact that they're all unique, I can go ahead and rank them. So if I think of my difference in atomic numbers, hydrogen is 1, carbon is 6, oxygen is 8, and bromine is 35. 35 is definitely my biggest number. So my bromine here is going to get my number 1 priority. Next is going to be oxygen. Oxygen is going to have 2nd priority because it has an atomic number of 8. Carbon is going to have 3rd priority, and then my hydrogen is going to have my last or my fourth priority. And this is our kind of ranking system that we'll want to figure out 1, 2, and 3, and 4, I guess. And these are going to be kind of our first problem, or the first step of solving these problems, going through and just getting our rankings. So if they're all 4 totally different and unique atoms, it should be relatively easy. It's really just looking at a periodic table and then giving them their specific rankings. Things can get a little bit more complicated though, because you don't always have 4 unique atoms that are directly connected. So if we imagine a pretty similar molecule to what we had, but a slight change here, where instead of that bromine, let's replace that with an ethyl group. So now I have a carbon, an oxygen, a hydrogen, and carbon as my 4 different groups. And here I see that I have 2 different carbons. Now, one of those carbons, the one on the right here, belongs to a methyl group. One over here belongs to an ethyl group. So those are different. So we still have 4 unique attachments, but the very first atom that's connected is not different for all of them. So what we'll do is we will still do our rankings as we can, but anytime we get to a tie, what we'll do is we will look at the things that are connected beyond that, and then we keep going and going and going until we find a point of difference. So in this example here, the first tier of highlights that I have here of my oxygen, carbon, carbon, and hydrogen, I can do some rankings. I know that oxygen is going to be the biggest because it has the highest atomic number out of those 4, so I can give that a ranking of number 1. And hydrogen is almost always going to lose, so that's going to be ranking number 4. But I can't do my ranking between 2 and 3 because both of them tie as a carbon. So because of the fact that they both tie, what I'm going to do is I'm going to look at the things that are connected to that carbon. So those are going to be these next groups here, which I just highlighted in green. And one of the things that you'll see that I'll often write is going to be something along the lines of this, where this is a carbon connected to a hydrogen, and a hydrogen. And I'm going to list out all the things that are connected to that yellow carbon, and I'm going to put these in order of my atomic number. In this case, they're all hydrogens, so I have nothing extra in terms of my rankings. And then here on my second one, I have a carbon, and that's connected to a carbon, a hydrogen, and a hydrogen. So this is my stuff here in yellow, and this is my stuff here in green. And here in terms of my brackets, or my parentheses, I'm going to write my carbon first and then my hydrogens later, and I'm going to have everything here in my brackets associated in terms of my atomic number, highest atomic number on the left, lowest atomic number on the right. So in terms of like thinking about these, if I look at my carbon versus my carbon, those tie. So I don't have any way to differentiate those. So then I look at the very next thing. And the very next thing here is going to be my carbon versus my hydrogen. And those are now different. So my carbon is going to have priority over my hydrogen. So I can give my ethyl my priority 2 and my methyl my priority 3. And it's important that we're only looking at the very first thing. So all of these extra hydrogens here, we're not considering, we're only looking for our very first point of difference. So here I can give my alcohol as priority 1, my ethyl as priority 2, my methyl as priority 3, and then my hydrogen as priority 4. Now, one extra kind of last consideration that we'll have with our CIP rules is thinking about multiple bonds, because there are double and triple bonds that exist. And anytime we have a double or a triple bond, we are going to count that as multiple bonds to the same atom. So a carbon-carbon double bond is going to be the same as like 2 carbon-carbon single bonds, for example. So let's go ahead and look at this example here. And I see that I have a chiral center, which is just that circle. And I see that there is a carbon, a carbon, a carbon, and a carbon as my 4 different groups that are attached to that. And those are all unique groups. Those are all different stuff connected to them. However, in terms of my CIP rules, we have a bunch of ties here because I have a carbon, carbon, carbon. I can go ahead and give my hydrogen my 4th group because that's going to be the smallest, but all my other carbons are going to tie. So I don't know how to rank my number 1, my number 2, or my number 3 just yet. So for that, much like we did last time, we're going to look at all the different attachments to those. So if I look at each of these carbons, this is connected to a carbon and 2 hydrogens. My top one is connected to an oxygen and a hydrogen, and my bottom one is connected to a carbon and a hydrogen. Now we can write out our kind of descriptions for all of these. And let's go ahead and start with the one on the right side. So my yellow carbon, and again, so this is going to be my yellow stuff, and then my bracket stuff is going to be my stuff here in green. In here, I am connected to a carbon, and I'm connected to a hydrogen. However, I see that I have a double bond here. And the double bond is going to count the same as two sets of single bonds. So I have a carbon to a carbon, which is my first bond. I have another carbon to a carbon, so I'm going to write this out as carbon-carbon hydrogen. So this is going to count as two carbon-carbon bonds, and then one carbon-hydrogen bond. So my overall description here is carbon connected to a carbon, and a hydrogen. If I do the same at my bottom left, I'm connected to a carbon and two hydrogens. That is my yellow and my green stuff. And then if I apply that same rule for my top thing, which is my aldehyde, I have a carbon that's connected to an oxygen, and then we're going to count that twice because of a double bond. So connected to an oxygen, and a hydrogen. So if I think about all of my different comparisons, carbon, 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 all ties. So I'm going to go and look at the next component. Here I see that I have an oxygen versus a carbon and carbon, and that oxygen is going to take priority because that oxygen has a higher atomic number than my carbon. So that is going to give this rank number 1. For my other two, I have a carbon-carbon, which are going to tie, and my first point of difference here is going to be my second carbon versus my hydrogen, making this my priority number 2 and this my priority number 3. And that's what we're going to do for our CIP rules. We're going to look at the very first thing and then give rankings. If I'm able to give rankings, 1, 2, 3, 4, I will. If I get a tie, and we're going to see a lot of ties with carbons especially, then what I'm going to do is I'm going to look at the next 3 things that are connected to it. And then if there's a tie, then you can keep going and going and going until you eventually find a point of difference. And eventually we're going to get our rankings of our 1, 2, 3s, and 4s, and those are going to be our unique attachments for each of these. And that's our CIP rules. We'll go to end the video there, and then in class we're going to focus a lot on using these specific rankings of 1, 2, 3, and 4 to find out our handedness, or that specific description of like R or S for our molecules.